Hello everyone, welcome to Energy Conversion 2 class. We are doing with chapter 3, that is Synchronous motor, and today's topic for discussion is effect of excitation on armature current and power factor of a synchronous motor. So, here is the phasor diagram. We will discuss one phasor diagram individually. We will go one by one. First, let us analyze it better way. Figure A shows the phasor diagram for EB equals to V. Here back EMF is equal to the supply voltage V. Here we can see this is the origin O. This is the voltage. Voltage reference is taken. Voltage phasor is here the reference. Now, current will obviously lag the voltage by an angle of phase angle phi. So, now, here is our back EMF EB. This line is also back EMF EB. Now, we will draw the resultant for V and EB. That will come here, that is resultant EMF ER. Okay, what happens in the second position? This is the condition when EB is less than V. At this condition, we will get an increased armature current, an increased power factor angle, that is phi is increased, and also we will see the angle between ER and I, that is theta position, is changed. Why? Because EB has shifted a bit towards this side. That is why our resultant EMF also changed its position. Here you can see previously the current was here with this minimum gap. Now the gap between voltage phasor and current phasor is being changed. Now what happens in the third figure? This is the condition for EB greater than V. What happens here? This is the condition for leading armature current. So, here armature current will lead the supply voltage by an angle of phi, that is phase angle, and also the position of IR will also change. Accordingly, EB will also change. And this is the condition for unity power factor. Here we can see the angle difference or the phase angle between voltage and current will 0 here. Voltage and current reference will overlap. Accordingly, ER will be changed. ER position will be this much, and now EB can be drawn here. Now we will go one by one. The value of excitation for which back EMF EB is equal to the applied voltage V. This condition is known as 100% excitation. We will now discuss what happens when motor is either overexcited or underexcited, although we have already touched this point earlier. Now, we have to consider a synchronous motor in which the mechanical load is constant, and hence it is clear that the output is also constant if the losses are neglected here. Now, going to the figure 2. So, what the figure 2 expressed? What about the figure 2 we will discuss now. So, first figure says that case of 100% excitation already discussed, that is the case of EB equal to V. The armature current I lags behind V by a small angle alpha phi. Its angle theta with ER is fixed by the stator constant, that is tan theta equal to XS by RA. What happens in figure B? Excitation is less than 100%, that is EB is less than V. Here ER is advanced clockwise and so is the armature current, but it lags behind the ER by fixed angle theta. We note that the magnitude of I is increased, but its power factor decreased. Why? Also, the power factor angle has increased. As a result, the power factor will be decreased. Because input as well as V are constant, hence the power component of I, that is I cos phi, remains the same as before, but wattless component I sin phi is increased. Hence, as excitation is decreased, we can say I will increase, but power factor will decrease, so that power factor component, that is I cos phi equal to OA, will remain constant. In fact, the locus of extremity of current vector would be a straight horizontal line as shown. Incidentally, it may be noted that when field current is reduced, the motor pull-out torque is also reduced in proportion. Now we can see figure C. It represents the condition for overexcited motor, that is, when EB is greater than V. So, what happens when EB is greater than V? We will see now. So, figure C represents the overexcited case we know. Here, the resultant voltage vector ER is pulled anti-clockwise and so is the armature current I. It is seen that now the motor is drawing a leading current. It may also happen for some value of excitation that the current may be in phase with voltage, that is power factor unity. Now, figure D shows it may so happen for some value of excitation, the current may be in phase with E, that is unity power factor case. At that time, the current drawn by the motor would be minimum. So, we can put 2 points as summary. 2 important points stand out clearly from the above discussion. The magnitude of armature current varies with excitation, obviously. The current has large value both of low and high valued excitation. So, it is lagging for low excitation and leading for high excitation. In between, it has minimum value corresponding to a certain excitation. The variation of current with excitation are shown in figure A, which are known as V curves. We will see later on slides. For the same input, armature current varies over a wide range and so causes the power factor also to vary accordingly. When overexcited, the motor runs with leading power factor and with lagging power factor when underexcited. But in between, the power factor is unity. The variations of power factor with excitation we will see. So, we will now discuss about the V curve. The power factor of the synchronous motor can be controlled by varying the field current IF. As we know that the armature current IA changes with the change in the field current IF, that is, with the change in the excitation. Let us assume that the motor is running at no load. If the field current is increased from this small value, the armature current IA decreases until the armature current becomes minimum. At this minimum point, the motor is operating at unity power factor. The motor operates at lagging power factor until it reaches up to this point of operation. So, if now the field current is increased further, the armature current increases and the motor starts operating as a leading power factor. The graph drawn between armature current and field current is known as V curve. IF and IA are considered to draw the V curve. If this procedure is repeated for various increased loads, a family of curves can be obtained. We can see here in this axis, in the x-axis we have taken field current IF, in y-axis we have taken armature current I or IA, and we know for armature current, different armature current values, we will get field current different values. So, this is the region for lagging power factor, this is the region for leading power factor, and this is the locus for unity power factor. Again, there are three conditions: full load condition, half load condition, no load condition. For both lagging and leading power factor, the armature current will be maximum. Okay, either leading or lagging, but the armature current will be minimum for unity power factor, we can see here. Now, the point at which the unity power factor occurs is at the point where the armature current is minimum. The curve connecting the lowest points of all the V curves for various power level is called unity power factor compounding curve. The compounding curves for 0.8 power factor lagging and 0.8 power factor leading are shown in figure above by a red dotted line we have already discussed. The loci of constant power factor points on the V curves are called compounding curves. It shows the manner in which the field current should be varied in order to maintain constant power factor under changing load. Points on the right and left of the unity power factor corresponds to the over-excitation and leading current and under-excitation and lagging current respectively. The V curves are useful in adjusting the field current, increasing the field current if beyond the level of minimum armature current results in leading power factor. Similarly, decreasing the field current below the minimum armature current results in lagging power factor. It is seen that field current for unity power factor at full load is more than the field current for unity power factor at no load. Now you can see the inverted V curve. So, this is the curve between power factor and field current. So, you can see here, this is the curve between power factor, field current. Field current is taken in x-axis and power factor is taken in y-axis. This is the case for no load, this is for half load, this is for full load. Again, this region is for lagging power factor, this region is for leading power factor. And we know both at lower power factor values, the field current value is like this. Okay, the power factor will be minimum in both the cases, but here the power factor will be maximum or unity. So, inverted V curves. The figure shows the graph between power factor and field current at different loads we have already discussed. It is clear from the figure that if the synchronous motor at full load is operating at unity power factor, then removal of the shaft load causes the motor to operate at a leading power factor. Thank you.